So I think we'll make a start now. Welcome everybody. Today we're going to be learning about reverse phase HPLC. Okay, so what we'll cover today is why reverse phase HPLC is particularly important in mass spectrometry. We'll look at chromatography basics. We'll look at isocratic elutions versus gradient. We'll look at the effects of column pressure, different types of column, how to select different types of column. We'll look at different types of connecting tubing and materials. We'll look at mobile phases. We'll look at junctions and dead volumes. We'll see how it's possible to deliver a stable gradient at very slow flow rates. We'll look at the hardware, and then we'll have a look at some troubleshooting. Okay, so HPLC, this is an essential analytical tool. It's also a preparative tool, and it's found in most wet laboratories. Operating HPLC, I would say, for a lot of biochemists and chemists, is an essential practical skill. And HPLC is very widely used. I've listed some of the uses here in pharmaceuticals, in organic chemistry, forensics, biological research, of course, and also in medicine. Very often HPLC is coupled to UV detection, but it's much more powerful if it's coupled to mass spectrometry. And that's been known for quite a long time, and most mass spec vendors also make HPLC equipment and vice versa. So reverse phase HPLC is absolutely critical in electrospray mass spectrometry. And the reason for this, I'm just going to get my pointer. The reason for this is basically down to ion suppression. Ion suppression is a big problem, or it was a big problem in mass spectrometry. And because of ion suppression, which can happen in mixtures of samples, mass spectrometry always works best when the samples are pure. And also in biology, most biological buffers are incompatible with mass spectrometry. So the purpose of HPLC is to solve these problems. So we use either reverse phase HPLC or SDS page, or usually both, to desalt the sample, remove small molecules, and separate the components of your sample so that they are delivered into the mass spec one component at a time. And this will give you very high data quality. And for this reason, electrospray mass spectrometers, they are always supplied with an HPLC. They're always connected up to an HPLC. And its job is sample cleanup, chromatographic separation, and automation. And this is known as hyphenation. There are different hyphenated mass spec techniques. This one is LCMS. And general thing to take away is the better the chromatography you can achieve, the better your mass spec results will be. So reverse phase is a particularly good separation. Usually this is done with peptides, and they're eluted using an acetonitrile gradient. It does a number of things. It, first of all, gives you excellent desalting. As we've discussed previously, desalting is very important. Reverse phase HPLC also has the highest peak resolving power of any liquid chromatography method. I've shown you a beautiful example of this in the illustration. The mobile phases are volatile. Not all HPLC mobile phases are volatile, but for reverse phase they are. That's extremely useful because they are therefore compatible with mass spec. Also, something you need to understand is the mass spec itself, generating a spectrum, is extremely fast. It takes milliseconds. But in comparison, the HPLC the mass spec is coupled to is relatively slow. So an HPLC separation may take minutes or even hours. But having said that, there have been many significant improvements in HPLC which has speeded things up tremendously. So there is nano-HPLC, ultra-high pressure HPLC, and also monolithic columns, which allow the system to run much faster. So apologies to those of you who've are already aware of this, but just to go over the basics in chromatography. So of course we have two phases. We have a mobile phase, we have a stationary phase, and they move with respect to each other. And any analytes in the mixture will partition into the stationary phase and also into the mobile phase, but they will partition differentially. So some components will preferentially partition into the stationary phase, and others will preferentially partition into the mobile phase, as I've shown here. And as the mobile phase moves across the stationary phase, then this differential partitioning results in peak separation. It's called reverse phase because there are two different types of chromatography. You can have normal phase chromatography, where you have a stationary phase, which is hydrophilic, and a mobile phase, or you can have a stationary phase, which is hydrophobic. So reverse phase chromatography uses this hydrophobic stationary phase. And the nature of that phase, that stationary phase, is it usually made up of silica particles. So this is effectively sand, and they are chemically derivatized with a chemistry on the surface. It's usually this chemistry. It's octadecyl silane, or ODS, or otherwise known as C18. So this is your silica particle. You have derivatized on the surface, and this is then packed into a column. This is a stainless steel column housing, and then we can pass our mobile phase through it. The mobile phase itself is part aqueous and part organic. And the compounds, they are can be either eluted from the station. Any compounds you add to this will absorb onto the stationary phase, and they can be eluted either isocratically or more commonly using a gradient of an organic solvent. And I'll explain that in a second. So isocratic elution, this means that the conditions of the elution do not change over time. So there is a single solvent. It's much simpler this way because you have a single solvent, you need a single pump, you don't need any complicated gradient controller. The retention time reproducibility is excellent. The peak width is not affected by the column dimensions, but the longer your retention time, as I've indicated here, the more peak broadening you will get, which is going to be undesirable. More common is gradient elution. So in this instance, in the gradient elution, the organic composition of the mobile phase will increase over time. So we need two solvents, we need two solvent lines, two pumps, and we also need a gradient controller because we're going to alter the ratio of these two solvents over time. Elution from reverse phase only happens when the critical mobile phase organic concentration is reached. So the peak shape, the retention time, these dependent on the gradient, the flow rate, and also the common dimensions. The peaks will elute sooner than on isocratic elution. We also have a very, very useful phenomenon, which is known as on-column concentration. So what happens is you can inject your sample in a very large volume, quite dilute, and all of it will bind to the column. And when you reach the critical organic concentration, it will all come off in one sharp peak. This is very useful. So this will generate tall, narrow, and well-resolved peaks. It's worth remembering, however, that in a gradient elution, you must re-equilibrate the column. If you don't do this, then your next injection will not necessarily bind to the column, could pass straight through in the void volume. So in order to re-equilibrate the column, you classically need to pass 3 column volumes of solvent through the column at the initial conditions prior to your next injection. And this is an example of a typical short HPLC gradient. There's a two-step linear gradient. In this region, this is maximum organic concentration. This is the wash region, and then this is the re-equilibration step. And you can see it's quite long, but the gradient itself is actually quite rapid. It's about 14 minutes. And this is what your gradient solution is going to look like. Solution occurs when the critical organic concentration is reached. Any polar compounds or salt, they will usually elute in the void volume. The hydrophobic compounds are, the more hydrophobic your compound is, the longer it will be retained on the column. And for peptides, which is what I generally use this for, larger peptides are also generally retained on the column for longer. So we know that chromatography is going to separate compounds in a mixture, but of course over time diffusion takes over, and those separated compounds are going to try and mix back together again. So to lessen the effects of diffusion, the faster the HPLC separation, the less effects the diffusion will have. So you can apply a higher mobile flow rate, and this will give you a faster separation and better resolution. However, the more you apply flow pressure onto the leading edge of the column, the more that pressure is resisted by the column itself. And this is known as back pressure. And this is, I would say, the primary limiting factor in liquid chromatography. So high pressure liquid chromatography and ultra high pressure liquid chromatography, these are systems which are actually designed to operate at extremely high back pressure. So to give you some idea, a gravity flow would have a pressure of a single bar. Fast protein liquid chromatography, this is between 50 up to about 50 bar. A typical analytical HPLC system would operate up to 400 bar, and a more modern ultra high pressure system can operate up to 1000 bar. So the higher the pressure, the higher the back pressure the system can stand, the faster the separation it can generate. So this is what an HPLC system looks like in its essential features. We have our solvent reservoirs here. They need to be degassed. There's a mixing unit. We have a high pressure pump. There's a switching valve and an injection loop. This is for you, enable you to inject your sample into the flow. Very often you have a guard column. This is the separating column. And then of course we need to have a detector. And you can very often divert the flow either to the detector or to waste. Here's a very primitive HPLC system from a very long time ago. I'm showing you this because you can see these individual components. So these are our solvents, A and B. We have a manual injection valve. You won't find these very often now. There are two pumps to deliver both solvents. Here's your guard column. This is your analytical column. We have a UV detector, and there is a gradient controller to manage these two pumps. And the data acquisition here is analog. This is done with a chart recorder. A more modern system would look like this. It's much neater, and it's also far more capable. So we have 4 solvents here in the solvent rack, variable wavelength UV detector. The columns now are housed in a column oven, and it has a switching valve, so you can select different columns automatically. This is very important. This was not present in the previous slide. This is the Autosampler, and this has a capacity for a very large number of samples that can be chilled in automatic operation. And this is your pump. This is a UPLC pump, and this can operate up to 1000 bar. So to say something about the mobile phases. So the mobile phases, they are either polar or they're organic. If you switch between a polar solvent and organic solvents, and particularly if that polar solvent has salts dissolved in it, it's always important to purge the system with water. Okay, if you fail to do that, when you switch to organic solvents, you can get salting out inside the system, and this can damage it. So in reverse phase HPLC, we always have solvents A and B. The aqueous one is by convention A, the organic one is B. The solvent A, the aqueous solvent, is usually millicube water. It could also be HPLC grade water or LCMS grade water, but the quality of the water is obviously very important. Solvent B, this is usually HPLC grade or LCMS grade acetonitrile. It can also be methanol, or it may be something else like isopropyl alcohol. However, the organic solvents, the purity of the water is very good. The purity of organic solvents is a bit variable. Very often they come contaminated with plasticizers and polymers. If you're doing UV HPLC, this is fine, but if you're doing LCMS, it isn't, because these will start to cause problems for you. So where you get your solvents from is important. Acetonitrile is probably the most popular solvent. That's because it gives the best resolution for peptides. Methanol is also very good. It's a slightly better solvent than acetonitrile, but the resolution is not quite so high. IPA, isopropyl alcohol, this is the very best solvent. It's less commonly used because it generates much higher back pressure. Also, in both solvents, you will need to add an ion pairing reagent. So these are added to the buffers at low concentration. Their job is to form ion pairs with any charged analytes, so they become electrically neutral, and those will give them increased affinity for the stationary phase. And this will result in higher resolution. So typical ion pairing reagents in HPLC might be trifluoroacetic acid, 0.01%. However, TFA is not used in electrospray. And the reason for that, it is an ion suppressant. So in electrospray, mass spec, LCMS, we use 0.1% formic acid. You will need to choose an HPLC column. You need to give some thought to this, because buying the wrong column, you're either going to waste money or more importantly, you're going to waste time. And there are multiple factors you need to consider, and I've listed them here: internal diameter, length, matrix type, functional chemistry, particle size, the pore size, the carbon load, the protein capacity, the column housing, the cost, and the column life. We'll go through all of these separately. So this is a HPLC vendor's catalog, and you can see there are dozens and dozens of different types of column. And choosing the column is rather difficult. What I would recommend is, if you have an existing working method, copy the column. Take the column from that method and just duplicate it. If you're not able to do that, I would, unless you're an HPLC expert, in which case you don't need to listen to this talk, I would seek expert advice. You can get this obviously from people who have experience of HPLC, but you can also approach the vendors and they will give you free technical help, and they will always help you choose the right column for your application. So let's look at some of these column features. Internal column diameter, or ID, this is important, and which ID column you use is determined by how much sample you have. So if you have a lot of sample or a small amount of sample, and it's also determined by the flow rate your HPLC can deliver. There are preparative columns. They will have a high capacity. They won't give you such good separation, and they generally cost more. So the more column packing in the column, the more it will cost. It's important to understand this point, that the sensitivity of any HPLC column is proportional to the inverse square of the column diameter. And I've shown you here some typical column diameters. This is a preparative system. Typically, people will use nanobore. For mass spec, it's more normal to use capillary or a nano system. But as the column ID gets smaller, the sensitivity of the HPLC dramatically increases. So the smallest ID columns would be 75 microns. To put that into context, typical human hair is 50 microns. So these are very, very, very small columns. Column length has a bearing. The longer the column, the better the separation. However, if you have a longer column, it's going to take longer to equilibrate in your gradient, and also your analysis time is going to take longer. You will need to load more sample, and the longer the column, obviously, the greater the back pressure. Also, the longer the column, the greater the cost. So these long 100 millimeter or 150 millimeter columns may cost twice as much as a shorter column. The guard columns, I'll explain what these are for in a minute, but these are very cheap, and you regard these as disposable. But columns in general are considered a consumable. And these are an example of different lengths. This would be a short column, this would be a guard column, and then there are different lengths of analytical column. Matrix, choice of the matrix is very important. There are effectively 4 different types of matrix, although there are all different types of variations of matrix. The main one, which is the original one, is derivatized silica, as I've explained before. The column is packed under pressure, and you can put different functional chemistries onto the surface of this. I've listed some of them. You can have different alkyl chain lengths. You can have C3, C4, C8, or C18. C18 is the most popular. This design of particle is where you have a solid core and then a porous shell around it. And you have the chemistry, derivatization chemistry on this porous shell. What it means is this has less resistance to the flow and therefore lower back pressure, which means you can do faster separations. Another way of doing faster separation is a column which is described as a monolith. So this is also silica. This is an electron micrograph of a monolith column. It's sometimes called a chromolith. And this matrix is grown in situ in the column. You can apply any chemistry to this matrix because effectively it's silica, so it's similar to the other particle based columns. The problem with monolith columns is they tend to be a lot more expensive and they have a shorter column life, but they will give you a much faster separation, which can be very beneficial. Final type of column is this. This is also a monolith, but this is not silica. This is made from a polymer. So the polymer is divinyl benzene. This polymer is grown in situ inside the column, and you can only have a single chemistry. So it's the chemistry that comes with this polymer, which is divinyl benzene. They tend to be more expensive than packed columns, but they have the advantages. The back pressure is very low and the column life is very long. So I've mentioned something about functional chemistries. Which functional chemistry you choose depends on what you are separating. These two, C3, C4, these will work for peptides, large proteins and macromolecules. You don't want your proteins to bind to these particularly tightly because otherwise it will not come off. So this is fairly weak binding for proteins. C8, used for pharmaceuticals and nucleosides and steroids. The most popular, as I said, is C18. This works for most things. Most organic compounds will bind to some extent to a C18 column. There are also end-capped columns. This is where the silane groups are trimethylized to stabilize the column, and this will reduce non-specific binding. As I've mentioned already, there's also divinyl benzene. This only really works for peptides. Particle size has a bearing as well. So a typical HPLC column particle size would be about 5 microns. You can get smaller particles, so there are columns which have a smaller particles. They will have a greater surface area and give you better separation. However, the smaller the particle, the greater the back pressure. So the back pressure, that increases with the inverse of the particle diameter. A development, I guess, in the last 10 years or so is UPLC. So this is ultra high pressure. These are special columns with very small particles, and they are designed to work with UPLC pumps. So these are pumps that can operate at a pressure greater than 400 bar. And the purpose of these columns is to allow you to do faster separations. Pore size is also important. So this is the gap in between the particles. The pore size, this 60 to 150 angstroms. This is suitable for small molecule separations. If you have a larger pore size, this is more suitable for proteins. The carbon load, you will see this listed in manufacturers' catalogues. And so this is referring to the percentage weight of carbon of the stationary phase. For example, how much organic material is actually chemically attached to the silica. The higher the carbon load, this usually means there's better retention for non-polar compounds. The loading capacity, this basically is telling you how much protein you can load on your column. So there is a maximum amount of protein you can load. Obviously, the smaller the column, the less protein you should load. When you've exceeded the loading capacity, your peak shape will deteriorate. And this is an indication that you've overloaded the column. Another indication of overloading the column is you will see carryover into the next sample. So you should choose an appropriate column for the amount of material you actually want to load. Column housing, usually it's stainless steel. It can't be stainless steel for monoliths and chromoliths because of the way they're manufactured. So they come in this thermoplastic housing. You need a special fitting. They're not really compatible with stainless steel fitting, so this could be a little bit of a problem. Sometimes these columns, these plastic columns, the housing can split. It can also delaminate, so this allows a flow path actually through the column rather than through the matrix. And they have these standard fittings. A standard HPLC fitting is 1/16 of an inch. So costs could be a consideration depending on how long your column lasts and how much money you have, how many analyses you want to do. Typical HPLC column will cost somewhere between £300 and £400. They cost more depending on if you're going to buy a special column. So if it's a UPLC column, it would probably cost double that. If it's a monolith, it may cost double that. Also, the larger the bed volume, the more packing material in the column, the more it will cost. There are ways to extend column life, and I'll discuss those. So your HPLC column is a consumable. It will not last forever unless you never use it. So you can, the lifetime of your column, it varies depending on a number of factors. So obviously, the more separations you do, the shorter your column life. It depends on the column type, as I mentioned. It depends on the nature of your samples. The more complex your sample, usually the more likely it is to block your column. And it also depends on how well you look after it. So there are column care aspects to HPLC. So what shortens column life? Well, columns can be blocked, or they can fail to separate because they get blocked by particulates. They can be overloaded. You should try to avoid this. If you fail to purge the column properly, if the column runs dry, this can be bad for it. How you store the column in between runs. So if you store it at the wrong pH or the wrong temperature or the wrong solvent, this will reduce your column life. As I mentioned, very complex samples can reduce the column life. Also, pressure shock. This is suddenly going up to very high pressure can shorten the life of your column. But you can make columns last a long time, and you can do this by centrifuging your samples to remove particulates and filtering any solvents. Obviously, don't exceed the maximum sample loading guidelines. You can find these in the manufacturer's notes or online. You can also pre-fractionate your sample, or you can deplete complex samples. This is especially important if you're working with something like a cell lysate or biological fluids like serum. Pre-fractionation, removing some of the more the compounds that are there in excess, will increase your column life. And you can use a disposable pre-column or a guard column. So what you do with this is this goes ahead of your separating column, and most of the particulates and things that will damage your column will be trapped on the guard column, and every now and then you can throw that column away and fit a new one. You can also increase the life of your column by back flushing, so you can reverse the column and use the vendor's recommended cleaning protocol to extend the column life. So your HPLC column is connected to the pump and to your UV detector or your mass spec detector by connecting tubing. And there are various materials you can use. They all need to be pressure resistant, they all need to be solvent resistant, and obviously chemically inert. So the original connecting tubing was stainless steel. This is very good. It's solvent resistant. It can make high pressure connections. Unfortunately, sometimes when you make these connections, the connection is deformed, so it's swaged, and you can't remake the connection. So once you've made the connection, it's fixed. Also, cutting different lengths of these is rather difficult, so you're stuck with whatever length you've got. Most HPLC systems don't use stainless steel these days. They use this material, which is PEEK. This is polyether ether ketone. It's a thermoplastic. It's resistant to almost all solvents. So it's chemically inert. You can put compression fittings on PEEK fittings, and you can remake them multiple times, which is very useful. It's very easy to cut, and so you can make your own tubing, and it also comes color coded because there are different diameters. That's important depending on what type of HPLC you're doing. Another type of tubing is this is fused silica. It's actually coated with polyamide. It's glass, so it's solvent resistant. It's very strong, so you can have high pressure connections. And it's typically used for nano-LC, so very low flow rates. You can make these compression fittings and you can remake them multiple times. You can cut it. There is a special cutting tool, a diamond tipped cutting tool you can use. The only disadvantage with fused silica is it's not particularly strong, so it can be very easily damaged. So, junctions and dead volumes. So typical HPLC will use stainless steel or PEEK fittings. So there is this is your PEEK tubing. This is where you're going to make that connection. And on the end of that, there is a ferrule. This is a cone-shaped piece of metal, usually metal. And when you tighten the nut, as is shown here, this will compress the ferrule onto the tubing and make your union. So ideally, this is called a ZDV union, so that stands for zero dead volume. And ideally, this is your dead volume where you have a little gap here. Ideally, you have no dead volume. However, if you're running at a high flow rate would be, say, 1 ml per minute, a 3 microliter dead volume, it won't really matter very much, so it's not a big issue at high flow rate. However, lots of mass spec uses nano-HPLC, and this means the flow rate is very, very, very low indeed. It can be as low as 80 nanoliters per minute, not microliters, nanoliters. So it's a very, very, very low flow rate because these columns are tiny. So these are made with capillaries, fused silica with an internal diameter of 20 microns. So this is half the width of a human hair. And I've shown you here a schematic of how the junction should be. So this is your fused silica capillary. That's the bore. You can see it's a 20 micron bore. It's tiny. There is a peak sheath around the capillary. This is your ferrule. And this is the stainless steel housing. And ideally here, there is no dead volume. However, if you have a 3 microliter dead volume here, I think you can see what happens at an 80 nanoliter flow rate. This volume will take 38 minutes to fill. And that means whatever gradient you had will be totally mixed. There will be no separation of your sample and there will be no chromatography. So dead volumes in nano-HPLC are a complete disaster. And making a junction of this type used to be very, very difficult to do. It required quite a lot of skill, and it was only really possible in quite advanced research labs. And one solution for this was actually to make a microfluidic chip. So this is a system developed by Agilent. You have a microfluidic chip, which you basically just plug that into the mass spectrometer. This technology has been around for quite a long time. It hasn't really caught on. People don't like expensive chip solutions. They like to make their own HPLC and choose their own columns and their own fittings. That hasn't caught on. What has happened is there have been a number of developments in UPLC connections. So UPLC connections, they have to stand very high pressure, up to 1,000 bar. If you have a poor connection, it will leak. If you over tighten it, you can crush the capillary because it's made out of glass. So what's happened is there is now a new generation of zero dead volume, high pressure connectors. And I'll give you some examples here. They are reusable. They guarantee there is zero dead volume. You cannot over tighten them. They tend to be quite expensive and they come in fixed lengths, but this is the way to go. I wouldn't really recommend learning the skill of making these junctions yourself. Much better to buy these. This is my favorite. This is a Viper made by Thermo, but there are others made by other companies. So you need to deliver a stable gradient. I say this because this is what's going on inside your HPLC pump. You have a reciprocating piston, and the flow is controlled by these check valves. But you will get pressure fluctuations. If you don't do anything about it, you will get pressure fluctuations because of this piston reciprocating. And these pressure fluctuations are referred to as ripple. And this is what it looks like. I've expanded the scale here at a high flow rate. So this is a flow rate of 1 mil per minute. This is the pressure. So I expanded the scale here. So this is 234 bar, that's 236 bar. And you can see over time this pressure fluctuation. And this is referred to as ripple. And it's about 1% of the pressure at high flow rate. And at 1%, it isn't a problem. However, as your flow rate decreases, if you drop it down below about 0.2 mils per minute, then this pressure ripple, which I've shown you another example here, this constitutes about 25% of the pressure. Okay, so that is unacceptable. This will not deliver a stable gradient for you. So there are a number of solutions. One of the earliest solutions to this was split flow. This is used for nano-HPLC. So how this works is you have a flow splitter. So this is where your input is split and it goes through two resisting capillaries. One of them has a high flow resistance, the other has a low flow resistance, and that will split the flow. So we start with a high flow rate and very little ripple. We split that flow, so it may be split from 1 to 100 or 1 to 1,000. And so 1%, if it's 1 to 100 split, 1% of your flow will go onto the column, and the other 99% of flow will go to waste. The back pressure will change due to alterations in the solvent composition. So we're running a gradient, the solvent composition will change, the back pressure will change, and those changes in back pressure can result in a change in the split ratio. So a simple flow splitter is not necessarily going to give you a reproducible gradient. One solution to this is to have this. This is so you have your flow splitter and you have a flow meter. So you have a bridge, a fluidic bridge in between these two capillaries. You have a flow meter, and that the output from that flow meter goes to a control valve, and that valve will be able to restrict the waste flow and keep a constant flow going through the column and to your detector. It's a very clever system. Unfortunately, it's rather unreliable and it's kind of falling out of favor now. Most nanoflow HPLCs now, they will use direct flow. So in a direct flow nano-UPLC pump, there are two pistons. They generate continuous flow, so they're always at positive pressure. There is no refill cycle. There is no flow split, so there's no flow controller to go wrong. It has multiple flow meters and multiple pressure transducers, and it does what's described as integrated control. So that enables the pump to deliver precise gradients at nanoflow rates. The flow is kept stable and it's independent of the back pressure or the temperature. It's a very, very clever system when it works. I'm just going to say something about detectors. UV detectors, there are different types. You can have fixed wavelength, you can have variable wavelength, or more frequently dual wavelength. You must know the absorbance of your analyte in advance. They're very good for quantitation. If you're using UV, the assumption you're making is the compound of interest will absorb at the chosen wavelength, and that's the only thing that is going to absorb at that wavelength. And that's not necessarily true. So this is one advantage of using mass spec rather than UV, is the mass spec will actually identify the compound for you. So UV, typically you would use 280 for aromatic amino acids in a peptide or a protein. If you use 214, this is less sensitive, but it's going to be present in any peptide or any protein. As I said, sensitivity at 280, this is usually much higher, but if you don't have aromatic residues in your compound, that's not suitable, so it's sequence dependent. The sensitivity is a function of the flow rate and the UV path length. So basically the flow goes through a Z cell. This part of the Z is effectively your path length. The longer that is, the more sensitive the cell. You're going to need an ultraviolet lamp to measure your UV signal. That lamp will age over time, so the sensitivity can deteriorate over time. If you have a low HPLC flow rate, as you might do on a mass spectrometer, you're going to need a much smaller flow cell. UV is less sensitive than fluorescence. But also UV detection, as I've said, it does not unambiguously identify your compound. And also it's not necessarily going to resolve different species with the same retention time. If they both absorb and they have the same retention time, you will not be able to tell them apart. HPLC systems, they often come with UV detectors, but because the sensitivity of UV is much lower, very often they're not used. You can have a diode array detector. So with the diode array detector, you are measuring absorbance at all wavelengths all through your analysis. So this gives you an extra analytical dimension to your HPLC. It permits qualitative analysis in addition to retention time. You can select the optimum wavelength for your analysis because you're measuring at all wavelengths. Yes, you can. Very often you will get different components that will elute at the same retention time, and so you will have a composite peak, but you can detect that with a diode array detector, which you may miss it with the standard UV detector. And also for small molecule analysis, when you're not sure what the absorbance is going to be, diode array detection is usually superior. So most HPLCs, I think probably all HPLCs now come with an autosampler, and this allows you to analyze hundreds or even thousands of samples without in unattended operation. Also, your autosampler, because you've got lots of samples, you may have samples sitting in the autosampler for an extended period of time, so it needs to be chilled. There are different types of vials. I'm showing you some different types of vial types here. These, depending on what it is you're analyzing, you can use 1.5 ml vials, 10 ml vials as standard, or you can also use microtiter plates. So you have here a syringe pump, and the purpose of the syringe pump is to operate the autosampler to fill the injection needle and to fill the injection loop. Injection loop can be any size from 1 microliter upwards, and these autosamplers, they also come with different injection routines, and the purpose of that, depending on what you want to do. If you want to inject a very small volume, or if you want to have very high reproducibility for quantitation, there are different injection routines. Most HPLCs will have a column compartment, sometimes referred to as a column oven. And this is because retention time can be very important in HPLC. And in order to replicate retention times, you have to be able to have a reproducible temperature. So very often, the temperature is just set at a few degrees above ambient so that it's reproducible. Another thing you can do is some columns will have a lower back pressure at higher temperature. One of the columns we use in the CMD, it's kept at 60 degrees rather than ambient temperature, and that reduces the back pressure, and so we can have a higher flow rate. You also, if you're going to maintain your column at above ambient temperature, you also have to have your solvents above ambient temperature. So they usually flow through a column heater, so a solvent heater, before they will go onto the column, so that they're at the same temperature as the column. You can have a switching valve here. This enables you to have one or more columns, which you can select for different methods that you want to run. So I mentioned retention time. Under controlled conditions, HPLC retention times are highly reproducible, and the retention order of your compound does not change. If you have standards that have been characterized well in advance, you can use retention time under defined conditions to absolutely identify compounds. There is lots of forensic work where compound identification is based entirely on retention time. In mass spec, there is a type of analysis called data independent analysis, and this uses the retention time of the compound along with its mass and also its fragmentation pattern to link the fragment ions to the parent. Let's say something about switching valves. There are different types of switching valves in HPLC systems, and this is what they can be used for. So you always have one in the sample loop. You can have a divert valve, so you can divert sample to waste from the mass spectrometer. You can select different columns. You can reverse the flow. This is an example of how you might do that. You can select different solvents, and you can also have a dual column method. So this is a dual column method where there is a trap column and there is an analytical column, and you can send sample onto the trap column and then reverse the flow and send it off the trap column onto the analytical column and then onto the mass spec. So just to say something about troubleshooting, most HPLCs will come with some kind of control software, and this allows you to identify any problems you will have with the hardware. If you have a problem, you need to learn to look at the pressure of the system, because this will tell you what it's doing. So the pressure readback is very crucial, because you can see if there's a leak, or if there is a blockage, or if there's some other problem. The pressure will very often tell you what's going on. And if you have a problem, what I would recommend is to work your way through the fluidic system. So work your way from the pump through the fluidic system logically until you can identify where that problem is. And I've given you some examples here of the type of problem you can have. For example, the instrument can shut down. The error is that the system has gone over pressure. That will happen automatically. And that can happen because the flow rate is too high, you have particulates, back pressure is too high, or the switching valve has failed. And here are some of the solutions you can apply. Another typical shutdown is the system has a leak. You need to identify, there'll be a leak sensor in the system. You can stop the leak, but you also have to dry the leak sensor. Otherwise, you'll still get that leak in error. If you get no peaks, this could be because the system is under pressure. There's actually no flow. There's no solvent. There's a pump failure. So the various solutions you can have to this. Sometimes if you have no peaks detected and you get this rapid pressure fluctuations. So I said you should monitor the pressure. If you see the pressure is bouncing up and down and up and down, usually the reason for that is because there is air in the system. So you can degas the solvents. Could be your degasser is not working, or you haven't purged the system properly. You can degas the solvents by sonication. You can also get air out of the system by running it at high organic solvent concentration. You can have problems because there is no sample. These can be sample-related problems. Concentration could be too low, there's simply not enough. Sample could be degraded, or sometimes you have an injection failure. So there's various solutions you can apply there. Sometimes you're not detecting any peaks, and that's because you have a chromatography failure. So you could perhaps have dead volume, as I already mentioned. Perhaps you could have no gradient because the solvent, solvents are not being delivered correctly. You can get unexpected peaks. This could be from contamination. You could have carryover due to sample overloading. Possibly have solvent contamination. This can be a big problem. Or you could have a faulty pump. If you have inconsistent retention times, this is usually chromatography related. So it could come from a faulty pump, faulty check valves. You could have the incorrect solvent, incorrect solvent proportioning. So this is not a list of everything that can go wrong, but this is a list of some of the things that can go wrong and some of the likely solutions to that. So that's really all I want to say about troubleshooting. And just to kind of summarize, HPLC, it is an essential practical skill. I can't emphasize that. It is a practical skill. It's especially important in mass spectrometry. At the end of the day, it's just plumbing. We've gone through the essential components of an HPLC system. We've looked at different gradients and mobile phases. We've discussed how to choose a column. We've looked at making HPLC junctions and how to eliminate dead volumes, which is a big problem in nano-HPLC. We've looked at nanoflow systems. and we've covered detectors, autosamplers, column compartments and switching valves, and we've had a brief look at troubleshooting. And before I finish, I just want to remind you, oh yes, it is of course just plumbing. Just remind you, next week in our final lecture, we will be talking about moldy mass spectrometry, and that will be on next Tuesday at 1 o'clock. And I'm very happy to answer your questions if you have any.